Hi guys, welcome to physics lesson 6.04 on centripetal acceleration. So we're going to switch gears. Up till this point, everything's been going in a straight line. Even gravity acts on a straight line. And this is going to be our first venture into circular motion. So let's start with an example, and I'm going to talk about a roulette wheel. So roulette is that game that they play in Las Vegas where you've got the little ball, and it goes in a circle around a track or a groove, and where whatever number it stops at is who wins. So we have this now, this little roulette ball is traveling with rotational motion. So we're now talking about rotational motion. Let's assume that it is spinning at a constant speed. So we're rotating at a constant speed. So my first question is, does this ball have acceleration? Take a second and think about it. Now, most of you said no, it doesn't, because what you're used to is if we have something that's traveling in a straight line, that means that the forces are balanced and the net force is equal to 0, and so there's no acceleration. Let's not forget that acceleration is a vector. Acceleration is a vector that has both magnitude and direction. Has both magnitude and direction. Excuse me. So we can change either the magnitude or the direction and have acceleration be present. So in this case, the magnitude's not changing. Let's say it's going at 10, we're going to use radians per second when we talk about rotational motion. So that might not be changing, but the direction is. At this point, I'm rotating this way, and if I'm here, my direction vector is going to go this way, and here my direction vector is going to go this way, and here my direction is going to go this way. So because I'm changing my direction at every moment, even though I have constant speed, acceleration is present. And that's a surprise because we've gotten used to thinking that as long as the speed, the magnitude is constant, there is no acceleration. Now remember, we define acceleration, average acceleration, as delta V over delta T. And we can talk about delta V as V2 minus V, or V final minus V initial, V2 minus V1, either way. So in order to talk about this intelligently, we have to talk about what is happening to the velocity of the ball, roulette ball, at each point. So let's draw a circle again. Oh, my poor circles. Okay, that started out as a circle. I'm not going to white that out. And the first thing we're going to talk about is, I have a thought question for you. Yeah, I can't stand it. I have to fix it. Or at least a close facsimile. So if this was opened up, and let's say we broke open the roulette wheel right here, what would, or how would the ball travel? So stop and give me a prediction. Most of you said that it'll continue on in rotational motion. Some of you might have said something a little bit different. So let's go to a video clip. We're going to look at this same scenario, but they put a marble in a pie pan. And let's see what actually happens. Let's see. I'm not sure. Give me a second. Yeah, I think it's going to be here. Yep. Okay. All right. Are you ready? So here's my marble, and we're going to rotate this. And when it hits this spot, it's going to, we're going to see what happens. Did you catch it? Let's watch again. It did not keep rotating. I have a better video. What they've done is they've taken a sparkler and they put the sparkler on a drill, and bits of the sparkler fly off. So look at the path the sparkler bits take. Do you see that they're flying off in a straight line? So contrary to what a lot of you thought, where that circular motion will continue, when something is released from circular motion, it leaves it in a straight line. Okay, I'm going to stop sharing my screen. The reality is, this is not what happens. When it's released, an object that's released from rotation will continue on in a straight line, and it does so in a way that's tangent to the circle. So most of you are in calculus, you know tangent is a straight line that butts up against a curve. So when released, our object continues in a straight line, in a line that is tangent to the curve. And I've got a video behind. Okay, I'm going to have to limit this and find out what's going on. Okay. Sorry about that. Okay, I'm still recording. I don't think I'm sharing my screen. I hope not. So when released, the object continues in a line tangent to the curve. So the speed that this comes, this is curve. The speed that this comes off with is called the tangential velocity. So it leaves with a straight line velocity, called tangential velocity. So I have, if I draw some smaller tangential vectors, and I'm going to do these in green. So here, if I would leave with this vector, and here I would leave with this vector. So we'll call this, let's call this V1. Let's call this V2. I'm going to go backwards. Well, we said up here that acceleration, so we're leaving with a straight line velocity, tangential velocity, and we said that acceleration is our final velocity minus our initial velocity. I wanted to do it the other way around. I wanted to do this as V2 and this is V1. I apologize. If I was going to add V1 to V2, I would do them head to tail. So if I was going to add this, I would do that. But that's not what I want to do. I want to subtract it. And remember, when we subtract a vector, we flip it. So when I go to subtract it, I'm going to draw the vector the opposite direction. So this here represents V2 minus V1. When I draw my resultant from the tail of the first to the head of the second, I get, so this represents my acceleration here. Notice it's pointing to the center of the circle. When we find the acceleration due to tangential velocity, the acceleration points to the middle of the circle. Now that's weird, and until we talk about centripetal force, it's going to stay weird. But turns out, if we take, and we write tangential velocity as VT. So if we take VT2 minus VT1, that gives us an acceleration vector that points to the center of the circle. Points to the center of the circle. Physicists called this centripetal acceleration. I'm going to abbreviate that. We usually write it as A sub C. A sub C. Centripetal translates to center seeking. And it doesn't matter. Anywhere you subtract the two tangential velocity vectors, that acceleration vector is going to point towards the center of the circle. So what this implies is that if we have acceleration going this way, we're also going to have a force. And the fact that the objects want to travel in a straight line when they leave, the implication is that objects want to move in a straight line always. So what are our implications here? The implication, I'm going to need more space, is that objects travel in a straight line unless acted upon by a force that, no pun intended, forces them to rotate. That forces rotation. Now, it turns out that in rotational motion, I scroll down to rotational motion. Rotational motion is highly dependent on the distance from the pivot point. Dependent on distance from pivot. Well, what do we call that? If I'm talking about my distance, my pivot points here. So if I'm talking about here to here, if I'm talking about here to here, well, that's the radius. That's the radius. So when we look at the formula for centripetal acceleration, it's a little bit different. It's not just delta V over delta T. And there's a lot more about rotational motion that we don't know yet. But our formula, and we abbreviate centripetal acceleration as AC, is tangential velocity squared over the radius. So we're just going to leave this here for now. We're not really going to talk about why until we get to rotational motion. But what you need to know is that radius always affects rotational motion. And if you've ever played the game Crack the Whip, we're going to watch a video of that later. You're going to see that it's really difficult for the person on the outside to keep up because their mechanics are very different than the person on the inside because their radius is greater. All right, so what are our takeaways? We're dealing with rotational motion for the first time, and something rotating at a constant speed still has acceleration because the direction is changing. When we release it, though, it moves in a line straight off of the circle called it's a tangential line. So we talk about the tangential velocity of an object would be the straight line velocity it would have when it's released. If we subtract these, the difference gives us a vector that points towards the center of the circle, and we'll get that for every point when we look at tangential velocity. We call that acceleration centripetal acceleration, and we calculate it by taking the tangential velocity squared divided by the radius. No sample problems here until we get through centripetal force. But that's all for this video. Thanks for watching.